We looked and said, okay, we know what will happen. So first we do a model. When you have Alice and Bob, and we say, let's assume there's symmetric traffic. So we are sending from both sides the same amount of traffic. And they don't have a direct connection, as I said before. Same amount of traffic is generated. And then the medium access control is based on IEEE 802.11, right? Which is CSMA-CA. It's important to understand that. Why is this important? If we look at a certain load scenario, right, where we have no XOR, no coding whatsoever, just thrown forward, and we say that Alice and Bob are generating a nominal capacity. What nominal means, we tested out what is the maximum traffic you can have there, was about 5 megabit per second, and we said 15% of that is sent to the relay, and the relay will achieve it and forward it. So whatever comes in goes out. This is store and forward, right? So what you will see here is, what we would like to look at is the throughput over the nominal load. And blue is with network coding and green is without. So what you see if you're here, 15% from both sides means 30% load. And what is the system capacity? 30%. No problem, right? If you go up here, 25% only they're sending. But as he is duplicating the traffic, now the nominal load is reached. So the channel is full, so to speak. So we go up to the point, and the question is, what would happen if we increase the load on both sides to 26%? Have any idea? Or say it with other words. You see, if you increase the load of Alice and Bob, the system throughput goes down. Why is this? It has to do with the medium access. So CSMA says we have a fair share of the capacity of the channel. So here, the relay has 50% and Alice and Bob 25. Everything fine. If you go here and they have 29, they will steal the capacity from the relay. Now you will say that's totally stupid because the relay is doing the job for them. But the relay doesn't know it. Not even Alice and Bob knows it in the bigger scenario, what they're doing. So what they will do is they will share the capacity until all of them get 1/3 of it. But if you get only 1/3, you can only forward half of it, what is the entry point, and your system capacity goes down from 50 to 33%. Now, what happens with network coding? You already see that we can reach a way bigger throughput. Why is this? Whatever comes in, 50% from the one side, 50% from the other side, now you XOR it and broadcast it. So only the relay eats up only 15%. And wherever you go, 25, now we didn't, at the same point we already filled it up with the standard approach. We could go higher. 29, there's another 29, still not higher than 100. Here we are higher than 100, and you see from now on there's no more capacity that we can get out. So now it's stabilized with 66%. And if you look at the coding gain, how much we get out, from this point it's equal, right? But from this point it goes up, and we are doubling the capacity. So this is the point. Before that we said Alice and Bob had 33% gain. But there's way more to gain if you think about protocols. So this was quite interesting, right? So just to send you again what really happens, we have the so-called activity chart, right? Alice is sending, then Bob is sending, and the relay sends twice if he also wants to send something in another scenario, right? Now here, what it does is send, and then he will broadcast just the information. And this is where network coding really kicks in. Now if you look at the activity model, what happens with the send activity with network coding and without network coding? So if you increase the load, Alice and Bob, as well as the relay, will go up until 33%, nothing happens. Without network coding, Alice and Bob both have the same load, but whatever they do, the sum of that is what the relay has to forward. And then it goes up to this point where you have 50%, 25 twice time is 100%, and from that on it will steal the capacity from the relay and the double rate that the Alice or Bob are using it until they stabilize at the same point as here. Now you could do the same not only with send activity but also with the receive activity. Alice and Bob are only receiving from the relay, and the relay will resend from both sides, so you know that they will send a lot of more with and without network coding. But here you see a little bit a dip. So for the relay it's the same, but Alice and Bob will first receive as same as here, but then the dip comes because the relay cannot spit out more packets, right? And if you have sending and receiving, there's something else, inactive or idle mode, and then you can just 1 minus sending and receiving, then you see the following curve. The relay with network coding goes down already at this point, has no idle slots anymore, fully busy. The Alice and Bob are then idle if the other side is filling up the relay. And here you have a lot of activity, a lot of idle on Alice and Bob because the relay is sending something but is not mentioned for them, right? Half of the time they are now idle. So if you then understand the different phases, what happens here, then in the first phase, from here to here, you can really say, okay, what is sending, what is receiving activities with and without network coding, right? What is doing Alice and Bob, what is the relay? We describe this in this table, okay? So this table shows you a little bit the 3 different phases. This is the phase where there's no difference in capacity from network coding or without network coding. Here is where network coding is still winning and where we are stealing capacity from the relay if we don't use network coding, and from that on it's stabilized, right? So far so good. For example, if you go through here, you can see exactly the points from this and this. This is the 1.5 L load scenario that you have. I think also for the exercise it will come, so you will go through a little bit in calculating this. Because now it's very nice to see what happens. Based on this activity charge now, you can look at the power model. So power model is the overall power that you will have is the power received with the activity factor of receiving, power level of sending with the power level of sending, plus the power level of idle and the activity factor of that. We measure this for the device, and as this is not a mobile device, this is just a platform access point, you have very high number of watt here, around 3. If you would have a mobile phone, this would be 1.1, receive would be 0.9, and idle depends, could be 0.02 if you really put it in deep sleep, or it would be 0.4, I think. And the maximum capacity of the channel, 5 megabit, as I said before. Now, this is now the power that we will use with and without network coding. Looks more or less the same, right? Because the relay is always doing something, the others are doing. Here in the end, there's a little bit, with network coding, we are using more power than without. Here we are using more because we are sending more, right? And we are receiving more. So therefore, here network coding is using a little bit more. So far, so good. If you then take the system power and the throughput, if you divide them, you get the energy per bit that looks like this, right? It's more or less a little bit, because the other one was quite stable, you get something out, they use more or less the same. In the first phase, in the second phase, they diverge, and then they will be satisfying at certain things like 6 microjoule per bit to 3 microjoule per bit. This is the theory. So what do you think is the actual reality look like in this case?